Hi, this is our 13th lecture, and we left off last time talking about the Untitled sequence, and so I will pick up there in just a second. But first I want to remind everybody, we got a homework assignment due on Friday, somewhere too. I've got your homework for everybody who's in this class right now. Your homework 1 rewrites grade. So I'm going to give those back into class. But don't forget we have homework 2 due on Friday. Did anybody want to ask any questions about homework 2 or ask any questions about anything that we've covered so far? Any questions from anyone?
So number 5, I was having trouble on.
Okay. So number 5 was asked about. Let's see if I have a copy of number 5, homework in general. I do. Right. So I'm very glad you asked about 5 or homework 2. In the problem itself, I think there's something to be altered. So for problem 5, homework 2, it says let script S be a subset of R, be non-empty and bound. And here's the change that I want to have made. Okay? Suppose A is a subset of S. This is what I want to put. That is non-empty. So I took this straight out of the book, but I think we need to say it's non-empty. Okay? And then we want to show the infimum of S is less than or equal to the infimum of A, which is less than or equal to the sup of A, which is less than or equal to the sup of S. So that's what we want to show, so people have asked about that. Okay, so here's what I would keep in mind, so some kind of hints. First, establish the existence of the nth of S, the sup of S, the nth of A, and sup of A. Give reasons why those exist as numbers. Okay, that's what I would suggest. So Adam, you were the person who asked me about this, is this correct? So once you have those numbers existing, then to compare these numbers, use the definitions of the nth of A and sup of A, and note characteristics of the sup of S and nth of S with regards to the set A. I don't think I moved the camera. Let me like that. I'll move the camera so people can see it. So, once you have the existence of the 4 numbers involved, then when we compare the
these numbers, we're eventually going to use the definition of the nth and sup of A. And what I'd like for you to do to help you make this comparison, what I would do to help make that comparison, is use characteristics of what the sup of S and nth of S have as numbers with regards to A. So sup of S says something about S, but it also says something about A because A is a subset of S. In particular, or for example, here's what I can tell you. If you look at the sup of S, that is going to be, so this is the least upper bound. So it's going to be greater than or equal to S for all S, little s, in the script S. Note, A is a subset of script S. So what does that mean? So for every A element of, for every little a that's an element of S, A is also an element, for every A that's an element of big A, that A is also an element of script S. That's what it means to be a subset. And if you're in script S, you're less than the sup of S. So that means for every A element of A is less than or equal to the sup of script S. And that tells me about something about the sup of script S in comparison to A, the big set A. That's what I'll leave you with, an example. So that's a hint, okay? Okay. So that's what I would be thinking about. Does anybody else have a problem, a question they'd like to see a little information about? It's okay to ask anything. Is it okay if I erase this left-hand side of the board? Anybody else with a question or comment? Well, before I move on to material, let me remind you that you're going to get a rewrite for this homework as well. But please turn it in on Friday. Let us move on then to new material, or progress with the concepts of the course. But first of all, let's recall where we were. We were talking about this M-tail sequence. So here's the definition. Given the sequence, this is a recall. Given a sequence X sub n, the M-tail sequence of X sub n is this sequence is X sub m, which is a fixed number, plus n moves, where m is some fixed natural number. So that's what we had. I wrote that down a little differently the first time that I listed it, but it's essentially the same. And as an example, if I look at the sequence 1 over n, as n runs from 1 to infinity, if I think of that as my sequence 1 over n, I mean x sub n, this is 1, 1/2, we did this before, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10, and so forth. Then the sixth tail sequence of 1 over n is, well, what it is, it's 1 over 6 plus m, 6 plus n, I should say, as n runs from 1 to infinity, which is the same thing as 1/7, 1/8, 1/9, and so forth. 1/10, and so forth. So essentially, we're removing the first 6 terms from the original sequence and starting here at the 7th and going forward. That's what it is. Well, I said that one of the things that this study of the entailed sequence, and we're not going to do much studying, I'm going to get one fact about it, and that's it, is that it emphasizes when we talk about convergence of a sequence, we're interested in what happens at the end. It doesn't matter what happens at the beginning of a sequence for convergence. You say, I know what the first billion terms are. We don't care. Billion is a small number when you compare it to going on forever. Does that make sense? A lot more numbers past a billion than there are before. So here's the main theorem, the only theorem that we're going to talk about for entailed sequences. And let me get this straight out of the text so that I don't miswrite anything. Okay. Theorem, it says, let x of n be a sequence, and m be an element of the natural numbers. Then the m-tail sequence of x of n converges if and only if x of n converges. In this case, the limit as n goes to infinity of the m-tail sequence is the same thing as the limit as n goes to infinity of the original sequence. They converge to the same thing. Okay. We will prove this. Brad, the first thing I noticed about the statement, truthfully, is that it's an if and only if statement. So that means I'm really going to have 2 proofs in each direction. So Chuck, that's what I'm thinking. Audra, I also noticed what they're talking about. They're talking about sequences and entail sequences. So John, I've got 2 directions to go. So we'll go in this direction. And what we mean by this direction is that we'll say the first thing, then the m-tail sequence converges. So suppose the m-tail sequence of x of n, x of m plus n, this is as n runs from 1 to infinity, converges. Megan, if we converge, if the sequence converges, it converges to a number. So that means there's some number that it converges to. Thus, there exists an x element of R such that, I'll just write down here, such that the limit as n goes to infinity of x of m plus n equals to x. So it converges to some number. Now, our goal in this direction of the proof, what we're trying to show? We're trying to show that x of n itself does what? converges. That's what I'm trying to do. And not only am I going to show that it converges, I'm going to show it converges to the same thing. That means I'm going to show x of n converges to x. Is that okay? So the idea is, hey, man, this tail end sequence gets really close to x. At some point in this sequence, the tail end sequence, all the terms are really close to x. Well, that means that after some point, it should imply, after some point, all the terms of x of n, the original sequence, are really close to x. That's right. That's what we're trying to do. Well, let's see how we do it. One of the beautiful things about mathematics, and in particular this course, is that we have verifiable methods to prove something. Mathematicians before us have written down and captured these ideas through definitions. What it means for the, after some point, for the terms of the sequence to be arbitrarily close to x. That's that definition. Okay. So here we want to show. Oh, sorry. We want to show the limit as n goes to infinity of x of n equals to x. And all I know is that the limit is n goes to infinity of x of m plus n equals to x. How do I show that the limit of a sequence is a particular number x? How do all these proofs start? Good. And what am I looking for? Okay. That's right, John. That's a spot. Well, it's a natural number, but it's a spot in the sequence. Such that for all spots beyond that, for all n bigger than or equal to k, the distance between x of n and x is less than epsilon. And the only thing I'm going to use is that the tail sequence converges to x. Tail sequence converges to x. So since the limit as n goes to infinity of x of m plus n equals to x, and I've been given an epsilon. Okay, so I know this is true. I've been given an epsilon. So for this particular sequence, x of m plus n, the tail sequence, there does exist a k. I'm going to call it k sub 1. It's an element of the natural numbers, such that for all n bigger than or equal to k sub 1,
I'm sorry. Should it be, we haven't said anything about m yet. We don't need to say it.
no, m is just a natural number.
Okay.
It's some fixed natural number. So for all n greater than or equal to k sub 1, the absolute value of x of m plus n minus x is going to be less than epsilon. So if I push far enough along in this sequence, all the terms from that point on are really close to x. That's what we're saying. Okay. And it happens at the k sub 1 spot where we're close enough for the epsilon that's given to us. Okay. So I'm going to come over here to the side, and I'm going to move the board in just a sec. Move the camera in just a second. But let's remember this 1 over n. Okay. This is our original sequence x of n that we use as an example. I'm going to let this guide us, help guide us to try to understand this. Okay, so I'm looking at this thing right here, which was 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10. Now, this, ladies and gentlemen, is a sequence we've already looked at. We know what it converges to. We've proven that it converges to something. What have we proven that it converges to? 0. So this guy converges to 0. Okay. Then the 6th, that's n equal to 6, tail sequence, here's what it is. It's x of 6 plus n, which equals to 1 over 6 plus n. 10 runs from 1 to infinity, which equals to 1. It's equal to 1/7, 1/8, 1/9, 1/10. Correct. Okay, it is going to converge to 0 as well. Okay, that's what this theorem is going to give us. But let us say we know it converges to 0. This part. That means that there's some spot in this sequence such that from that spot on, all the terms of the sequence are within epsilon units of whatever it converges to, which is 0. So let's say I say I want to be within 0.1 units of 0. Where would you have to go to make that happen from then on? It would be at the 11th position. Is that okay? From the 11th position on, all the terms of the M-tail, the 6-tail sequence. Okay? Well, I shouldn't say the 11th position. That's wrong. 12. No. To be within the 10th, it happens at 1 over 11, 1 over 12. But what position is that? That's 1, 2, 3, 4, 5. It's at the 5th position. Is that okay? So here in my work on the board, the case of 1 will be 5. If I go to the 5th position here in the parent sequence, the original sequence, I'm only at 1/5. I'm not within 0.1 units. So what do I have to do to translate this to get me to the same output value? I'd have to not be at the 5th position, but the 11th, which really is the same position we had here.
Plus m.
That's right. So it's case of 1 plus m. Is that okay? So that's what I'm thinking of. So here's what I'll say. So we let k be equal to case of 1 plus m. Then, I need to move this back over. Is that okay with everybody? So for the original sequence, if I go to the k plus 1, case of 1 plus m, then for all n bigger than or equal to k, x of n minus x will be less than epsilon. Thus, x sub n as a sequence converges to x. So if you go to the case of 1 plus m spot in the original sequence, you get the same term that you did in the case of 1 spot in the m tail sequence, which was close enough. Is that okay? And every term beyond that was close enough in the m tail. That's what we have. Okay, that's part of the proof. That's the one of the forward direction. Now we need to do the backwards direction. So in the backwards direction, we assume or suppose the limit of the original sequence, so n goes to infinity, of x sub n equals to x. What do we want to show? We want to show so what did the statement say? What's the other direction?
The M-tail sequence converges.
All right, we want to show the limit as n goes to infinity of x of m plus n equals to x. Then it converts. Not only is it going to convert, it's going to convert to x. That's what we're going to show. How do I show that a sequence converges to x?
Epsilon greater than 0.
That's correct. What do I need? We need a, I won't call it k again, even though we're having two k's. I'm just thinking of them in like two separate proofs. We need a k element of natural number such that for all n bigger than or equal to k, the absolute value of x of m plus n minus x will be less than epsilon. And all I'm getting to use is that the original sequence converges to x. Well, let's use it. Since the limit as n goes to infinity of x of n equals x, and I've been given an epsilon, then there exists, and I'm going to call it k, a k element, let's call it k sub 2, element of natural numbers. I call it k sub 2. Such that for all n bigger than or equal to k sub 2, the absolute value of x of n minus x will be less than epsilon.
Let's go back to our example, see how that helps us.
Let me give everybody a second while I fix that. Okay, so look, we're assuming that the original sequence converges to something else. So I've given you an epsilon, and we say, hey, there's a spot. Let's say this spot on, the 11th spot, as we did before. So it's the 11th spot. That's my case of 2. From that spot on, all the terms of the original sequence are really close as I wanted of what it converges to. Is that okay? X. How far would I have to go in this sequence? Well, really you could say I go to the 5th spot. You know, if you wanted to, you could say it's case of 2 minus m. Is that okay with everybody? But you could just say I'd still go to the kth spot here, and that's what I'm going to write. Because what if I go to the 11th spot here? What output value am I going to have at the 11th spot? I don't know. Let's see. So at the 11th spot, I'm going to be 1 over 17. Is that okay? So the 11th spot is 1 over 17. Is that okay? And isn't 1 over 17 really close to whatever it converts to? More than what this is close to what we converted to. So pushing along to the same spot in the tail sequence really pushes you further along in the original sequence in terms of the output value, which you already know was in epsilon distance of what it converges to. So I'm going to say here, we let k equal to k sub 2, then for all n bigger than or equal to k, x sub n plus m minus x will be less than epsilon. And that concludes the proof, so I'll make a conclusionary statement. So this sequence, x of n plus m, converges to x. And that's it. I want to say just one more thing of the way what we just wrote this part of the proof. And you can kind of apply that to the other direction, the first part of the proof. But here's what I'm going to point out. I want to have your attention. You know what this is telling me? This tells me as long as the index is bigger than k sub 2, you guys see where I'm pointing? As long as the index is bigger than k sub 2, the x of that index is within epsilon units of x. Okay? As long as this index is bigger than k sub 2, etc. Okay. So here, if you take n's that are bigger than k sub 2, what about this index? This index is something that's bigger than k sub 2 plus a number. So that means this index right here is bigger than k sub 2. And if you're bigger than k sub 2, which is what this is telling us about, then its distance from x is less than epsilon. And that's a way of thinking about it. Is that okay? That is the way that I think about it. All right, so that's that proof. The next thing I'm going to do is write up one more fact. And it's going to be a fact that's going to come up later in the class. We're going to use it later in the class. But it has to do with the showing that the sequence converges. And again, I won't write it straight out of the text. Okay. So here's what it says. So it's a theorem. And it says, we let x of n be a sequence. Of course, when we say a sequence, we mean it's an infinite sequence of real numbers. And we let x be an element of R. Now, if a sub n is a sequence of positive terms, positive numbers, okay, with the limit as n goes to infinity of a sub n equaling to 0, and if for some constant c that's greater than 0, and for some m element of natural numbers, we have the following inequality, that is x sub n minus x inside absolute values is less than or equal to a sub n times c, and that's true for all n bigger than or equal to m, then what we could say is the limit as n goes to infinity of x sub n has to be equal to x. I'm going to move the camera and I'm going to start the proof, and the start of the proof is going to be assuming the if part of these things. So a lot of the proof is going to be, at least the beginning, restating what we have. So I'm going to let x sub n be a sequence. Suppose, and I'm going to let x be a real number. I'm going to suppose there exists an a sub n with a sub n being greater than 0 for all n. So there's a positive sequence, and there exists a c that's positive, and there exists an m element of natural numbers such that for all n bigger than or equal to m, we have the following. That's that x sub n minus x is less than or equal to a sub n times c. We want to show that x sub n converges to x. Let me give everybody a second to write it down.
Look, I want to show x sub n converges to x. Well, we kind of have a boilerplate setup to try to prove that. We start off by, how do I show x sub n is going to converge to x? What's our proof setup? Somebody besides John. What's the first thing we say? Go ahead, Audrey. That's right. So that's a distance, okay? And what are we looking for? What do we need? We need what, Chuck? Okay. I need a k. That's a spot, okay? So it's a natural number such that for all n bigger than or equal to k, so all terms of the sequence beyond that spot k, their distance from x is less than the positive number that was given to us. Brad, look, I want the distance between x sub n and x to be small. That's what I want. But here's what I know. I know the distance between x sub n and x is less than this quantity. So if I want to make this small, really, if I could make this be small, it would force the smaller guy to be small. Does that make sense? So if I can make this be less than epsilon, we get it. Does that make sense? If this part's less than epsilon, then this part has to be less than the smaller part has to be less than epsilon. So that's what I'm going to concentrate on. Well, this statement here isn't always true. It's only true for n values bigger than or equal to n. Okay, so we've got to keep that in consideration. And if here's what I'm thinking. If I want to make this be less than epsilon, okay, this be less than epsilon. C is a constant. It doesn't change. So I can't make it get small. C is whatever it is. The way that I can make a sub n times c be small is to make a sub n get small. Is that okay? Well, what's going to allow me to make a sub n to be small? Well, what are the a sub n's converging to? Zero. So that means I can make the a sub n to be really small. Does that make sense? How small do they need to be such that when I multiply them by c, I get less than epsilon? So in essence, kind of scratch work here. I want a sub n times c to be less than epsilon. What does that mean? That means I want a sub n's to be less than epsilon divided by. Is that okay? That's what I want. Okay. That's what I want. I'm going to erase that. That's my goal. So here, I'm going to start with it. Since the limit as n goes to infinity of a sub n equals to 0, then there exists a case of 1, element of the natural numbers, such that for all n bigger than or equal to case of 1, this a sub n minus 0 will be less than whatever I wanted it to be. And what did we say that we wanted? It wanted to be less than epsilon over c. Now wait just a second. So really, I'm using the definition of convergence of a sub n. That's what I'm doing. And so I've got to be given an epsilon. My role of epsilon, the distance, is really not epsilon in this case. It's really epsilon over c. This is like my new epsilon for this problem. What do we know about these distances? They got to, or the epsilons. What do we always say about them? We always say let epsilon be given, let epsilon be greater than 0. Okay? So they got to be greater than 0. How do I know that this is a distance, a possible distance? How do I know this is bigger than 0? Well, I know epsilon is greater than 0. What do I know about c? Greater than 0. So if I divide two positive numbers, I get a positive number. Okay, so that's playing the role of epsilon, if you will. And okay, thus, I'll write right down here. I think I got enough. For all n bigger than or equal to case of 1, well, let's talk about a sub n minus 0. I'm going to do two things here. What is a sub n minus 0? A sub n. Now, wait a minute. What about the absolute value of a sub n? The absolute value of a sub n is either itself or it is minus a sub n. It's itself if a sub n was what kind of number? Positive. It's minus a sub n if a sub n was negative. But what do we know about all the a sub n? They're all positive. So here, for all n bigger than or equal to k, I know that a sub n is less than epsilon over c. Okay. Okay, that's where I am. Okay. Now, what I had just written had to do with n's being bigger than or equal to k. And I want to use that other fact about x sub n minus x inside absolute values being less than the a sub n times c. But that fact isn't always true. It's only true for n bigger than m. And the thing that I just wrote about a sub n being less than epsilon over c, that's not always true. It's only true for n's bigger than k sub 1. I want to have one spot where both of those things are true. And we did this once before. I want to see if anybody can remember. How far do I have to push along? I don't push to necessarily k sub 1. I don't push necessarily to m. I have to, if I want both of the things to happen. So, the maximum, that's right. You have to push far enough along in the sequence that both happen. Is that okay? So I'm going to let k equal to the max. Oh, we're taking it to the max now. Okay. Then, for all n bigger than or equal to k, we have the absolute value of x sub n minus x is going to be less than or equal to a sub n times c. That's from the given, the thing I was assuming. Because if you're bigger than k, you're bigger than m. Is that okay? But this is going to be less than a sub n for all n's bigger than or equal to k. If you're bigger than k, you're bigger than k sub 1. So the a sub n's are going to be smaller than epsilon over c. And then I still got times c, which equals to epsilon. So for all n bigger than or equal to k, that particular k that we found, x sub n minus x is going to be less than epsilon. It's going to be less than epsilon. So I was given epsilon. I found the spot in the sequence that fit all the terms. From that spot on, distance from x was less than epsilon. What does that tell me about the sequence itself? Say it again, Hope.
That converges to x.
That's that it converges to x. And that's what I wanted to show.
Question.
Yes, sir.
Where did the extra factor of c come from in that?
In here,
Oh, okay. So you're just substituting epsilon over c. Okay.
yes. So John was asking this question. He says, okay, look, we know this is a given. Okay, it's something we're assuming. Then, well, where's this coming from? Well, here, this c is this c. All I'm doing, John, figure it out, is I am substituting in for a sub n something bigger than it. What's bigger than a sub n? C over epsilon. How do I know that? Because of this fact that we got. Is that okay? Right here is maybe a better place to point to. That's how come I can make that place. So I'm taking positive quantities, I'm multiplying them together, and I'm saying, hey, that's less than this other bigger positive quantity times the scale. I mean, essentially, look what I'm erasing. Don't we know a sub n is less than e over c, or epsilon over c? So if I multiply both sides by a positive number, don't I maintain that inequality? Mm-hmm. What positive number am I multiplying by? It's okay, John?
Yes, sir.
Good. It's a good thing to ask about. That's the way I'm thinking of it. That ends this proof. Go ahead. Anybody with a question about what I've done so far? Well, what would you think if we just got out 6 minutes early today? Well, you should be thinking you're dreaming because it didn't go happen. Think something like that. Next thing we're going to talk about is bounding. I think we'll talk about bounding. Let me look again. Either that, or we'll talk about. We're going to talk about the additions. Yeah, we're going to talk about a bounding sequence. Oh, this is nice. So here's the definition.
You may want to change the camera.
Thank you very much. I was going to do that, Chuck. I was just making sure people would help me. Here's the definition. A sequence
X of n is said to be a bounded sequence. Listen, what's a bounded set? Stop. Give yourself a chance. And it's okay if you don't get it. I'm asking Melissa, but I'm asking all of you. What's it mean to be a bounded set? So, you know, in our homework, we got S is a bounded set. What's that mean? It means it has an upper bound and a lower bound. That's what it means. Okay. So what does it mean to be an upper bound? That's a number out there that's bigger than everything in the set, bigger than or equal to. What's it mean to be a lower bound? That's a number out there that's smaller than or equal to everything in the set. So here, the sequence X of n is really an ordered set, so it's a set. So what I need for it to be bounded is I need something that's bigger than it and something that is less than all of them. Is that okay? The way we're going to write that is if there exists an m bigger than 0, John, such that the absolute value of X of n is less than or equal to m. So Brad, the reason this is good enough to give an upper and lower bound is if X of n inside absolute values is less than or equal to m. That means X of n is less than or equal to m, but it's bigger than, say it again. Negative what? No? M. Remember, what I'm using there is if we have the absolute value of A is less than or equal to C, that means that A is sandwiched in between C and... That's right. That's exactly what we're moving. So M is an upper bound for the X of n's, and minus M is a lower bound. That's what they're saying, but this is the way that they're summarizing it.
Is that for all n?
And that's right. It's for all n element of natural numbers. So we're almost done with the definition, but that needs to be added. Okay. Well, let me write up this statement that we're going to prove. So it's a theorem. If X of n is a convergent sequence, then X of n is bounded. That's something we're going to prove, okay? And we're going to prove it next time. That's the statement we're going to prove. I'm going to tell you the idea of it. And next time we're going to start off with me recalling this definition, and I'm going to do some examples, okay? And then we're going to state this theorem again, and then we're going to prove it. But that's what this is kind of preview. So wait just a second. Why would X of n be bounded? So you think about the terms of the sequence, where they are on the number line. If they converge, why are they going to be bounded? Well, what does it mean to converge? It means they get really close to a certain number. Okay, so after some point, all the terms of the sequence, after some point, are really close to this certain number x. Is that okay with everybody? Well, what about the first few terms? Well, they're scattered about. They can be wildly away from x. But it doesn't matter. They're just a few of the terms. You bound those few terms, and then you bound the ones that are really close to x. And so you can't be going off towards infinity or minus infinity in either direction if you converge. That's the idea. Before we move on, before we call it quits, can you give me a bounded sequence? 1 over n is bounded. What's it bounded between? It's bounded between, well, your m could be 1. All the terms, the absolute value of 1 over n are less than or equal to 1. I'll tell you another bounded sequence. Minus 1 to the n. What did it bounce between? Minus 1 to the n. Remember, it was 1 and minus 1. So all the absolute values of each term is less than or equal to 1. They're less than or equal to 50 as well. Is that okay? Beautiful. See, we're going to have to stay longer. That's right. So what does this statement say? It says if you converge, you are bounded. But just because you're bounded doesn't mean you... That's exactly right. So that's a big thing. If you converge, you're bounded. But if you're bounded, you may or may not converge. It doesn't imply convergence being bounded. And that's an example. I'm going to list that next time, okay? All right, look, we need to get our homework back because you guys want to go on to the next class. And I'm going to close now.